Thank you very much. Thanks for having me. Yeah, so I want to talk about sort of some of the latest research in zero-knowledge proofs, and we can later on, talk about how this can be used for, hopefully could be used as in a ZK opcode or something like that. And yeah, I just want to show you sort of like where the research is heading. I don't have a lot of time, so I'll skip over a lot of details, but just in general to show you kind of what is possible and what sort of the most recent developments are. And yeah, I guess the specific paper is called Accumulation Without Homomorphism. And in particular, this is a proof system for so-called sequential computation. So imagine you have some sort of input, and then you iterate, some function on it many times. And this actually, okay, this seems somewhat abstract, but what could this function be? Well, you can just imagine this function to be a virtual machine. So something like the EVM or, some RISC VM or some sort of arbitrary VM, and then you can actually encode any sort of a program on type of that VM. And one other thing where I think this could actually be very interesting for ZK rollups is that you can always sort of continue the computation. So at any state of the computation, or at any point of the computation, do I have a mouse? Don't have a mouse, okay. At any point of the computation, I have a state xi, and then I can continue the conversation from that state on. So I can, then iterate my VM one more step, one more block, and then I get to the state xi plus 1. And my goal is to prove that this computation was done correctly. So I could use a snark for it, where I basically, I run the computation for 4 steps, and then I produce a snark that the computation was done correctly. The problem is, if I do this, if I then do one more step of the computation, I have to recompute the entire snark, right? And this may be very expensive, and also I need to remember the entire history of the entire computation in order to do this. So it's not memory efficient, it requires additional steps to reprove everything. So the solution to this is something called incrementally verifiable computation, where at any point of the computation, I take the current state of the computation and approve, and then basically I prove that the next step of the computation was done correctly, and I can also I can increment the computation, and I can also increment the proof. And the idea is that at any point in time, I can take the current computation state, xi, and the current proof, and update it without having to remember the entire history. And at the end, there's some verifier that accepts it, but even at this point, I could continue the computation. So you can basically stop the computation at any time and check that it was done correctly. And the goal is that the proof is basically the proof size, and the prover and runner time should be entirely independent of the length of the computation. So there are many approaches for constructing, or there's sort of 2 different main approaches for constructing IVC. So one of them is snark-based. So essentially this is sometimes referred to as recursive snarks. So what I do is I prove that I know a snark of the previous step. And this is very expensive. So this has some pros and cons. So for example, let's focus sort of in I could build this like from Starks, so I could use recursive Starks or recursive Frye-based proofs. Then one advantage is that I can use hash-based cryptography, which is relatively fast, sort of per gate. And you can use small fields, and it has post-quantum, but it has a big overhead, which is that it has sort of this so-called high recursive overhead. So what I would need to do is I would need to prove that a previous Stark was correct. And that step alone, it's constant size, but it is a massive constant. Like it adds 1 million gates basically to every proof that I want to do. So this is the big downside, is this recursive overhead. And then on the other hand, we have these very new accumulation of folding-based techniques, which at a very high level, they avoid a lot of the snark machinery, they have some benefits, and in particular, they have a very low recursive overhead, so it's only about 10,000 gates. But on the other hand, it uses group-based cryptography, so something based on discrete logs, which has two key downsides. The first one being that it's slow, sort of per gate. The cost per gate is slow. Like it has fewer gates, but the cost per gate is slow, or slower. And the other big downside is that it's not post-quantum. So the goal of this work is basically to get the best of both worlds. So to get this part here from the top, and get in particular this line here from, I'm showing my mouse. So get the snark-based, the fast hash-based cryptography with the lower recursion overhead. And hopefully this would allow you to design better sort of better IVC schemes than either of these approaches before. And again, I talk about IVC as this special case, but it turns out that IVC is actually general enough to build arbitrary snarks for arbitrary computation. So if we can really achieve this, and if we can get this fast enough, then this might actually be the best way of building a snark for a general computation. Okay, so can we build accumulation of hash-based cryptography? And I guess the one thing that I want to tell you about these accumulation schemes is the idea is basically of these accumulation schemes is that if I have multiple proofs, say I have many proofs, what I can do is I can combine these proofs into an accumulator. So I can always take, say, two proofs, or like I can take a proof and a current running accumulator, and then basically just add this proof to the accumulator and continue doing that. And the idea is that at each step there's a so-called accumulation verifier which doesn't check that the previous proof was correct, because that would be an expensive operation. That would be as expensive as checking a snark, so that's expensive. But instead it just checks that this proof was correctly added to the accumulator. And it can do this every time, and then in the end there's this so-called decider which checks the accumulator, the final accumulator. And essentially the idea is that if this final decider accepts the final accumulator and the small accumulation verifier accepted every step, then all of these proofs are valid. And I can use this, at a high level, I can use this to also build an IVC scheme where at every step I just run the accumulation verifier inside the circuit. So instead of doing a recursive snark, I do a recursive sort of accumulation verifier. And that's a much smaller box than running the entire snark verifier inside of the circuit. There's some, sort of some properties here. I don't want to go into the details. Basically, the key idea is that I want to construct these accumulation schemes because they give me IVC. I'll skip over exactly how this works, but please trust me on this working. And I guess the key point is that the size of the accumulation verifier, sort of the size of this purple box here is, oh, it doesn't really come as purple, but of this box should be as small as possible. And our contribution was that we were able to build accumulation from hash-based crypto. And the reason why this is interesting is, I'll just go to the next slide and show you why this is interesting. Well, so what does accumulation in the past rely on? Well, essentially, all that the accumulation does is it takes a random linear combination between sort of the current proof and the current accumulator. So I have basically I have two strings. One of them corresponds to the current proof, and then I have one to that corresponds to the current accumulator, and I take a random linear combination between them. And the way that this is done is that I have something called a homomorphic hash, or homomorphic vector commitment. So this is a short string that corresponds to this long vector. But if I have two of these short strings, I can add the short strings, and I get a hash of basically of the addition of the long strings that were hashed. So this homomorphic vector commitment is the key point. The problem is, how do we construct these homomorphic vector commitments? And essentially, the only way we really know how to construct them, or the only way that we know how to use them, uses this group-based cryptography. So this is where this group-based cryptography comes in. However, as I said before, this group-based cryptography has some downsides. It basically is pre-quantum, so it could be broken by a quantum computer, and it is inherently slower than using sort of pure boring hashes, something like SHA-256. So the goal was to get rid of this homomorphism. So this is the goal of this, this talk. And I'll give you the very, very high-level idea. So the idea is that instead of basically, say I now have 3 vectors. So I have this vector w, I have this vector z, and I have this vector w prime. And I want to check that w prime is equal to w plus alpha times z. So previously, I would use the homomorphism to just check that this is correct. But now I can't do this anymore. So what I do is I write down these vectors, and I commit to them using Merkle trees. So I have a Merkle tree of each of these vectors. And then what I do is, instead of checking the homomorphism directly, I'll just check it at random points. So I'll sample a bunch of random points here. So this is sort of a query set. And I check that the homomorphism holds at these points. And if the homomorphism is correct, then it should hold also at random points, right? So that's the benefit. But however, there is a big problem, which is, well, okay, let's say first what the intuition is. Well, let's say that the homomorphism only holds at half of the points. Well, then with every query, if those queries are random, I have a 50% chance of checking, basically finding a bug in this, right? So say it holds at half of the points, then I can just do one query and I have a 50% chance of catching the adversary. And if I do enough queries, then basically the probability that I catch the adversary is incredibly high. So I can do, you can do some calculation and basically figure out where the adversary is, that the adversary is cheating. However, what if the adversary cheats at just a single point? What if there's just a single inconsistency? Well, it turns out then then you will basically not be able to have enough queries to catch that point. So our idea was to use something called linear codes or error-correcting codes, where we encode the messages. So we basically make the message a little bit longer, such that even if there's basically errors in the message, you can still decode, sort of even from a noisy code word, I can still decode to the original message. And it turns out that if we do this, that even if there's, well, even if the homomorphism only holds at, let's say, 50% of the points, after decoding, it turns out the homomorphism will hold everywhere. So these linear codes, they basically protect us from these errors that we don't catch in these linear checks. There's one final issue that I want to address, which is that if I do this over multiple steps, I'll get more and more errors. So if I have one code word in the beginning, then after one step, a malicious prover may be able to insert one error. And then if I do this 2 times, then I'll have 2 errors, and so on and so forth. So I can only support basically a bounded number of accumulations. And you might wonder, well, this isn't very helpful. Say I want to do like a 1,000,000-step computation or like a 1,000-step computation, then this becomes problematic. Well, it turns out that it's okay. And the reason is that we can build something called bounded depth accumulation, and we show that bounded depth accumulation is still enough to construct IVC. And essentially, the idea is a very old one, comes from like a paper from 2013, and we sort of give a bunch of optimizations for it, which is instead of a line, in general in computer science, when sort of a line or a vector doesn't work anymore, build a tree. And that's exactly what we do. So instead of building a line, we build a tree. And the benefit is that the tree has much lower depth than the line, right? If you follow any depth here, this is only logarithmic in the size of the length. And basically through that amplification, we can get a much higher, and we can support higher arities and make this work to basically make this much more practical. And we give a bunch of other optimizations as well. So that's sort of the final slide. I want to sort of say that this bounded depth accumulation is very interesting because it could potentially give us really, really fast proof systems. And the core idea is that we can use basically Merkle trees and linear codes in order to successfully emulate the homomorphism instead of doing it directly. The final thing that I want to talk about is sort of 2 future directions that we've been working on, which I think are very interesting. One of them is, can we get unbounded accumulation, even from these hashes? So the approach that we took currently only gave us bounded accumulation, and it seems like we would need sort of somewhat different approaches in order to get unbounded accumulation, but we're actually quite hopeful that we can do this, so that we can get unbounded accumulation even from hash-based primitives. And this would sort of get rid of a lot of the complexities with having to build a tree and so on and so forth that sort of this current work has done. So stay tuned for that. And then another thing is basically related to the accumulator size. Yeah, I'll skip over that. That's a pretty technical issue, but also an interesting one. So yeah, you can find the paper online, and happy to sort of discuss this work more. And yeah, it's a very technical topic, so which I had to present in a very short time. But hopefully, sort of, at least I piqued your interest that there's sort of a lot of cool research happening in this space, and a lot more work to do, and we can actually achieve sort of I think that one of the things that excites me about it is that I think we can get the best of all worlds if we work hard enough on it, which is sort of post-quantum and fast and small enough, hopefully. And yeah, there's obviously still some trade-offs, but there's also a lot of progress being made. Thank you very much.